Hey guys, in this second video we're going to talk about some more advanced topics in molecular geometry, once again relying upon valence shell electron pair repulsion theory, but now looking at situations where you have more than 4 bonding groups. So a quick recap, remember valence shell electron pair repulsion theory, or VSEPR, allows us to build upon the Lewis model and predict geometry or three-dimensional arrangement of atoms rather than simply the connectivity or bonding that the Lewis model gives us. So remember, our first step in understanding geometry is to build that Lewis model and then use VSEPR to predict the geometry. And VSEPR is simply the idea that electron groups repel one another, so the geometry that is adopted is the geometry that minimizes this repulsion or maximizes the separation between electron groups. And all, doesn't matter what kind of electron group you're dealing with, they all are subject to the same idea of electrostatic repulsion. So lone pairs, single electrons, single bonds, or multiple bonds, they're all going to try and arrange themselves geometrically to get as far away from one of the other electron groups as they possibly can. Okay, so we were left then with this idea of maximizing separation as our sort of guiding principle of VSEPR. And so all we have to do is look at our central atom in a given Lewis dot model, determine the number of electron groups around that central atom, and determine how many electron groups or lone pairs and bonding pairs there are. And you can then back out, based on this geometric arrangement that minimizes the repulsion energy, the actual geometry. And we mentioned previously how there's essentially 5 different options in terms of electron geometries, how these different groups can arrange themselves. Previously, we talked about the first 3. In this video, we're going to talk about the last 2. We're going to talk about trigonal, bipyramidal, and octahedral geometries. So once again, I want us to turn to our simulation. So go ahead and follow the link in your lecture slides or given here on the screen to open up the simulation, and let's start building up some examples. Okay, so hopefully you have your simulation open here. So the first thing we want to do is start adding in some bonding groups. So previously we went all the way up to 4 different bonding groups, okay, and this was our tetrahedral geometry. Now, our first step here is going to be to add 1 additional bonding group. So I'm going to go ahead and add a 5th bond. And as you can see, adding that 5th bond, of course, distorts that tetrahedral geometry. Everything's 109.5. And now when I add that 5th bond, we end up with a geometry that looks like this. And there's some very important characteristics here that are different from what we've seen previously, right? The first thing I want to show you is that if we orient things, this almost looks like a jack or something that you play jacks with, right? You have this sort of group, linear group, kind of going right up down the center. We're going to call this the axial group. That you effectively see a 90-degree separation, a 90-degree bond angle between these axial groups that I'm highlighting here with the mouse, right, and these so-called equatorial groups that are right here around the equator. So if we're kind of rotating around the equator, right, we're seeing that 90-degree separation. Now, if we rotate this molecule and we look right down the axis of those axial groups, we see that we have effectively a trigonal planar configuration right around that equator, or 120-degree separation between those equatorial bonds. Okay, so basically the corresponding geometry, or trigonal bipyramidal, is essentially a linear geometry and a trigonal planar geometry kind of smashed together here. And this is the optimum geometric configuration for maximizing the separation between these 2 or 5 different electron groups. Okay, so going back to the slides here, we see that again 120 for those equatorial groups right down here, and 90 for those axial groups right along that axis. Okay, so an example of a trigonal bipyramidal geometry would be phosphorus pentachloride, PCl5, right? Illustrated right here, right? Where I've taken some time to go ahead and label those equatorial chlorines and axial chlorines. So axial is up top and down here at the bottom. Okay, so we've got two axial chlorines, and then of course the equatorial, I'll circle in green here, we've got three of those equatorial chlorines. Okay, so if we go back to our simulation here, take our 5 electron groups and now add in a 6th electron group, a 6 bond, well, once again, we're going to smash the atoms even closer together, and we're going to end up with a configuration here that I think actually might be what a jack looks like. That'll be your homework assignment here, where you basically have 90-degree bond angles between every single one of these bonding groups. Okay, and this is called an octahedral geometry. For obvious reasons, right, if you connect the dots for all of these atoms, the vertices will be the vertices of a polyhedron. You end up with an 8-sided polyhedron or an octahedron. Okay, so a little bit prettier illustration of that, right here, where we can see the octahedral arrangement, 90-degree bond angles between all of the atoms. And so an example of this is sulfur hexafluoride. Now I want to point out here, a very common mistake I'll see students make is, they try to label atoms axial and equatorial in an octahedral geometry. So I'm going to point you back to this simulation again, and consider I'm going to put my cursor right here by this atom. If I were to rotate this, you close your eyes, rotate it 90 degrees, rotate it 90 degrees, no matter what I do, it's the exact same molecule. There's no difference between axial and equatorial in this case. They are all equivalent atoms, all 90 degrees away from one another. Okay. All right. So then the last thing to do now is to take these trigonal bipyramidal and octahedral geometries and ask the question, well, what happens if we introduce lone pairs of electrons? Okay, well, if we have 5 electron groups and we have a single lone pair, we're going to end up with something that we call a seesaw geometry. And so we can visualize this going again back to our simulation. I'm going to delete one of the bonds, put in a lone pair, and you end up with something that looks right like this. Okay, and so if you kind of, it's going to be a little hard for me to do. You can kind of consider it like kind of a seesaw moving back and forth. Okay, so this guy goes up and down, up and down. Okay, so can't visualize. It's a little hard to move around there, but this is our seesaw geometry. Okay, now the important thing here that I really want you to see is the location where that lone pair went, and we'll go ahead and turn off the bond angles. They're kind of getting in the way there. So notice that I'm basically taking these axial atoms that are still in place. That lone pair went in an equatorial region. And the reason for that is it actually minimizes repulsion. Remember in the previous lectures we talked about how lone pairs occupy more space close to that atom because they're fatter, right? That a bond, the electron density is distributed between the two atoms. Lone pair, it's all taking up room right around that central atom. So it needs more room. And if you look at the seesaw geometry here, where you've put that lone pair in an equatorial position, the result is only 2 90-degree penalties with the 2 axial atoms. Okay? If we go back and look at our slides here and consider what would happen if we put that lone pair in a axial position, we'd end up with 3 90-degree lone pair bonding pair repulsion, so 3 penalties. So here, by placing that lone pair in that equatorial position, right, we only have 2 90-degree penalties, and so we end up with our little seesaw geometry. Okay, so then as you'd expect, if we were to take out one of those bonds and replace it with another lone pair, we're of course going to put that second lone pair also in an equatorial position, and that will give us a T-shaped molecular geometry. So once again, we still have 5 groups, so it's a trigonal bipyramidal electron geometry, but the molecular geometry is now T-shaped. Okay, so the T shape here is exemplified by the BrF3 molecule, where you end up having 2 lone pairs on that central bromine atom, and the corresponding T-shaped molecular geometry is illustrated here on the right-hand side. Now, if you carry out this process one last time, switch out that final, that third bonding group with a lone pair, and then we end up with a structure that looks like this, which of course is a linear molecular geometry with all 3 of those electron groups occupying equatorial positions. So an example here is the XeF2 molecule that we built in a previous lecture in the Lewis-Stott structure, illustrated right here, and the corresponding electron and molecular geometry. Now finally, we want to consider what happens if we take that octahedral geometry and start replacing bonding groups with lone pairs. Well, it turns out that if you construct 6 electron groups with only 1 lone pair molecular geometry, you end up with something that is called a square pyramidal structure. And you can we're illustrating this with the example of BrF5. Once again, we can turn to our simulation here, and we are considering a situation where we have a total of 5 bonds, right, and 1 electron group. And you can see here how all 4 of these bonds are kind of forming the base, a square base, where this 5th bond pointing straight up would be the top, the vertex of a pyramid. So you've got square pyramidal structure for that molecular geometry. Okay, so of course, remember, it doesn't matter when you're replacing that first bond with a lone pair here in an octahedral geometry. It doesn't matter which one you take off because they're all equivalent. Okay, but now if we were to play the game of removing another one of these bonds and replacing with a lone pair, now we've got 2 different options. We could either replace one of the base bonds in the base of the pyramid or the one on the vertex. And so the thing that you have to keep in mind here, once again, is that these electron lone pairs end up taking up more room. So our objective here is going to be to keep those lone pairs as far away from one another as possible, which is going to be accomplished by putting them on opposite sides of the base of that pyramid. And once you do that, then you end up with 4 bonding groups, right? And they're all in a plane with lone pairs on either side, and they're forming a square, so we call it square planar, a square planar geometry. Our example of a square planar geometry right here with this XeF4 molecule illustrated on this slide. Okay, now of course we could continue that, move to T-shape, move to linear, just as we did before. You guys get the idea, and I encourage you guys to play around with the simulation and really get a feel for what these different geometries look like. So here's our summary then. Just as we saw for our first set of geometries, I'm breaking it down to number of electron groups over here on the left-hand side, and the number of bonding lone pair and the corresponding EG and MG electron geometries and molecular geometry. So of course, if there are no lone pairs, we're left with trigonal bipyramidal. For both, we already saw PCl5 as our example. You introduce 1 lone pair, you take that equatorial position, put the lone pair in there, you end up with a seesaw molecular geometry. Pull off 2 bonds, replace them by lone pairs. Both lone pairs occupy an equatorial position. You end up with a T-shaped geometry. And finally, we saw how that linear geometry results if you end up putting a total of 3 lone pairs. And then finally, if you have an octahedral electron geometry, 6 electron groups, right? You pull off one of those electrons, one of those bonds, you place it with a lone pair of electrons, you end up with that square pyramidal, and you pull off another one and we get our square planar geometry that we saw previously.